When you use numbers that have uncertainties in a calculation, the result of the calculation is also uncertain. Because of this, you should avoid to keep more digits in the final answer than necessary. Consider the following rules in your calculations to make sure you get your significant figures correct. First, multiplication and division. Even though the rule we're about to discuss can also be applied to division, we will explain the concept using this example for multiplication. The area of a rectangle with dimensions of 12.3 centimeters long by 4.5 centimeters wide is 53.35 centimeters square. Do we have to keep all of the digits in the number 53.35? This is what you usually do using a long multiplication process to multiply these numbers. The digits in blue in 12.3 and 4.5 are the least significant figures for those numbers. These digits are uncertain and affect the multiplication process. And as you can see from here, the final answer is affected by this uncertainty. The digits in blue in the final answer are all uncertain. In the final answer, the first digit is the most significant figure, but the second digit is already uncertain, and therefore is the least significant figure. This is a rough general rule if there is no detailed information of the uncertainties. In multiplication and division, find the least number of significant figure used in the calculation. This number must be the number of significant figure in the final result. Example: 12.3 has 3 significant figures. This number is multiplied by 4.5, which has 2 significant figures. Clearly, 4.5 has less significant figures than 12.3. The least number of significant figure here is 2. As a result, the final answer should also be expressed in 2 significant figures. 2. Addition and subtraction. Again, the rule we're going to discuss holds true for both addition and subtraction. But we're going to use addition as an example. Adding 5.67 centimeters and 8.9 centimeters will give us 14.57 centimeters. Consider this for a moment. Although 5.67 centimeters is accurate to about 0.01 centimeters, 8.9 is only accurate to about 0.1 centimeters. How is it possible that the final result is more accurate than 0.1 centimeters? From this, we learn that when adding and subtracting, the number of decimal places matters more than the number of significant figures. And this is the rule we have for this case. In addition and subtraction, find the least number of decimal places used in the calculation. This number must be the number of decimal places in the final result. Example: we add 5.67, which has 2 decimal places, with 8.9, which has 1 decimal place. The least number of decimal places in this case is 1. Therefore, the result should be rounded so that it has only 1 decimal place. In the previous 2 examples, you can see that you need to round off a number so that it has a certain number of significant figures or decimal places. And this is how you round off numbers. Suppose we want to round off pi to a certain number of significant figures. In the first example here, we want to round off pi to 3 significant figures. First off, we cut off the number to the required number of significant figures, in this case 3. The first and the most significant figure here is the digit 3. The second is 1, and the last digit is 4. So the 4 here, written in blue, will be the least significant figure. Then, we treat the rest of the digits as a fraction in decimal, adding 0 point in front. And the resulting fraction in this case is 0.1592 and so on. Next, we compare this fraction with 0.5. If the fraction is more than 0.5, then we add 1 to the least significant figure. But if the fraction is less than 0.5, we do nothing to the least significant figure. And since in this case the fraction is less than 0.5, the final result is 3.14. We do nothing to the 4. Second example. We now want to round off pi to 4 significant figures. Again, we cut off the numbers to the required number of significant figures, in this case 4. So in order to have 4 significant figures, we truncate the number in between 1 and 5, as you can see here. The last digit written in blue here is the least significant figure. The second step, we treat the rest of the digits as a fraction in decimal by adding 0 point in front of the remaining digits, and the resulting fraction is 0.5926 and so on. Then, we compare this fraction with 0 0.5. Since in this case the fraction is more than 0 0.5, we add 1 to the least significant figure. As a result, rounding pi to 4 significant figures, giving the result 3.142.